Okay, hello everybody, welcome back. We're going to push forward now into chapter 4 where we start to talk about different types of probability distributions. We're going to focus on something called a discrete distribution today. But before we talk about that, let me mention quickly what we mean by a random variable in statistics and in this course in particular. So we've been talking a lot about different kinds of probability experiments, these being experiments where I have some sort of list of outcomes and the outcome is determined by chance. So this could be something like pulling a name randomly from our set of data is one that we did a lot, or something like pulling a card from a deck or something to that effect. And in these cases, what we can do is we can start to associate the different outcomes of our experiments to numerical values, counts or measures. And oftentimes there's a very obvious correspondence, in particular when these outcomes themselves are counts or measures. So what this is essentially is just a function. We're mapping the input of our function is in fact the outcomes, and the output is some kind of numerical measure or count. And so a random variable is just this association. It's an association which is taking the different outcomes of an experiment and associating them to numerical values. And now it sounds complicated, but it's really not. And if I think about a very simple probability experiment like rolling a die once, I throw a die once and I have a list of outcomes that could occur. And to each outcome, I have a very natural way to associate a number to those outcomes. In particular, if I roll a die, I know I can get a 1, 2, 3, 4, 5, or 6. And so I can associate each outcome with its number, 1, 2, 3, 4, 5, or 6. And that's a random variable. It's a function. It's a map taking my outcomes to these numbers. And why do I want to do that? Well, there's another number that goes along with each of these outcomes, and that's its probability. So for each outcome of this experiment, I have a numerical value, which represents the size or quantity of the outcome, and I have a probability. So for each number, 1 to 6, there's a corresponding probability. The probability of me obtaining that outcome. The probability of me rolling a 1 is just 1 out of 6. The probability of me rolling a 2, it also happens to be 1 out of 6. And so the association of these values of a random variable, i.e. the outcomes, to their probabilities is what we call a probability distribution. Okay? When I have outcomes, and these outcomes have numbers or measurements somehow, and I associate those measurements to their probability, and I display it in a table or a graph, this is what a probability distribution is. So for example, I can take the outcomes of my die roll, 1, 2, 3, 4, 5, or 6, and I can associate them to their individual probabilities of occurring. And in this simple example, each outcome has a probability of 1/6 of occurring. So this table right here on the left, this is a probability distribution. Basically, what does that mean? It means it shows me just all the probabilities that go with each outcome of a probability experiment. And that whole random variable stuff that I was talking about is just a method of ensuring, in some sense at least, that these outcomes not only are outcomes of the experiment, but they have some sort of numerical measure to them, right? So I can think about these numbers as representing the size or the quantity of my outcomes, and this is the probability of each of these happening. And this is a probability distribution. It's a display of the outcomes of a probability experiment along with the corresponding probabilities. And I can display it either as a table, or of course if I have a table with numerical values on both the x and the y-axis, then I can make a nice good looking graph to go along with it. So this graph to the right represents also the same probability distribution. I can display it as either a graph or as a table. I say up here it can take the form of a graph table or some other description, it doesn't matter. But as long as it's showing the outcomes to their corresponding probabilities, it's a probability distribution. And just one quick note on this word discrete probability distribution. In mathematics, mathematicians actually make distinctions between the sizes of different infinite sets. I won't talk about it very much. If you want to listen to more about countability and cardinality of sets, of infinite sets, you can come see me in the math seminar where we talk about this kind of stuff in our junior math seminar. But of course I don't think anyone's going to come see that, but you can, you're welcome to. Look on the schedule and please drop in any time. But basically, in this class for for our purposes, if a set of outcomes of a probability distribution, or the random variable itself has only a finite set of outcomes, we'll refer to our random variable as discrete. On the other hand, if our set covers some portion of the real number line, so if we're talking about all the possible outcomes of my experiment can be any number between some range and some range. So for example, if the outcomes of my experiment are something like heights, then I'm assuming that people can be any height between, say, 5 and 6 feet. Then my outcomes cover an entire portion of the number line. We'll call those continuous random variables, okay? And if the set is is infinite, but does not cover a portion of the real number line, there's other distinctions here, but then that means, I don't know. Okay, and just a quick word on how we'll make a few distinctions one distinction between different types of random variables. If our random variable has only a finite number of outcomes, then we'll call it discrete. Finite number of outcomes meaning that the probability experiment that we're associating with this random variable has only a finite set of outcomes. Then we'll call it discrete. And also if it has an infinite set, but that infinite set can somehow be put into correspondence with the set of natural numbers. This is what's called countable in mathematics. We don't need to worry about this too much. If you want to know more about countability and the cardinality of sets and infinite sets, it's a very interesting topic in sort of elementary analysis. You can come see the seminar if you want, Math 397. We talk about this kind of fun stuff in the math seminar. But for our intents and purposes, random variables will be discrete unless the outcomes of that experiment can somehow be represented as a portion of the real number line. So a fun result from advanced mathematics shows that any portion of the real number line that you take, if you take a continuous portion of the real number line, it is not countable, it is not discrete. It can be not put into correspondence with a set of natural numbers. So things like heights or weights or something, where we're assuming people can be absolutely any height between 5 and 6 feet, these are not discrete random variables. I think most of the random variables we deal with in this course will be either a finite set of outcomes like we have here, or an infinite set. But just so you're not confused when you see this distinction, it's a little bit more finicky than that about what we call discrete and continuous. Anyways, lots of talk, but let's see an example of a probability distribution. So it's not always as simple that we can make it just off the top of our heads 1/6, 1/6. So this is a nice example. I did this in class, so I won't go through it all here. But this is a probability distribution, this table over on the left-hand side. And I have a situation here where I'm considering the number of Mexican-American jurors that could appear on a jury of 12 people from a town where 80% of the people are Mexican-American. So assuming that people are randomly selected from a town which has 80% Mexican-Americans, I can calculate the probability of obtaining 0, 1, 2, 3, and all the way up to 12 Mexican-Americans in that selection of 12 people. And the probability distribution is just a table which shows the likelihood of me getting that many Mexican-Americans on my jury, assuming that it's selected completely at random. So I read this table by saying things like the probability of getting 6 Mexican-Americans on a jury, again, assuming that they're selected from this town at random, where 80% of the people are Mexican-American, is 0.016, so 1.5% about. The probability of getting a jury with 10 Mexican-Americans is about 28%. The probability of getting between 6 and 10 Mexican-Americans is the sum of all these numbers. So it looks like about 40, 51, 61, 64, 69. It's somewhere around 70%. So I have about a 70% chance of getting between 6 and 10 Mexican-Americans on my jury. So this is what a probability distribution is. Again, it's just showing, I think about this probability experiment as being the selection of a jury in this particular town. There's different outcomes. I've classified my different outcomes based on how many Mexican-Americans there will be on the jury. And this probability distribution is just a table that's showing the likelihood of each outcome happening. And again, I can show this either as a table or as a graph like I have down here on to the right. And so you can answer all kinds of questions on this. So for instance, if this stuff is true, it's very interesting in fact. So let's suppose that this is true and this is a town with these properties, 80% Mexican-American. A Mexican-American man is sentenced to life in prison by a jury which has only 50% Mexican-Americans on that jury. Now, what might happen in this case is his lawyer might go and say that this is unfair. This man has the right to be tried by a jury of his peers. And in a town of 80% Mexican-Americans, we should expect that his peers will be approximately 80% Mexican-American. So, if he was tried by a jury which had only 5 or less Mexican Americans on it, well, you might say that's possible. I mean, the jury is selected at random. Maybe we just randomly picked only 3 or 4 Mexican Americans and the rest were non-Mexican American. And so, if you were a judge and the lawyer appealed and said, this jury is clearly biased, there's, only 6 of 12 were Mexican American, I want this case thrown out of court. I want a retrial. I want a mistrial. The judge has to ask himself, what's the likelihood that this jury has only 6 Mexican Americans strictly by chance? And if I look at this probability distribution, of course, calculating these probabilities is a trickier exercise in theoretical probability. You have to be very good at counting to do this. The judge could determine that, well, in fact, it's only about a 2% chance. I could look at my graph right here and say, 6 is right here. Only about 2% of all juries selected from this town, truly selected at random, should be selected with less than 50% Mexican Americans. So is that enough evidence? If you say, well, I don't know, that's up to you. That's up to the judge to decide. Is this evidence that there's bias? 2%? I mean, if I had a 2% chance of winning the lottery, I would play quite frequently, right? In 100 trials, you're going to get at least 2 with only 6 Mexican Americans. On the other hand, maybe the judge feels that this is evidence of bias. But this is an interesting question and can be thought about just by looking at our little probability distribution. Anyways, one last example, and then next time we'll talk about expectation and stuff like that. So here's an example. Sony conducted a study by grouping 4 people, and by stopping groups of 4 people, and counting how many of them recognize Sony as a brand name. So in this particular case, we can associate a random variable, x, as representing the number of people out of 4 that actually recognized Sony. And so if x is the number of people that recognized us in our little group of 4, x can be either 0, 1, 2, 3, or 4. And the probabilities, according to the study, just based on the tabulated data that we don't have here, is 0.002, 0.03, and so on, and so on. So make a probability distribution for x quickly, and then find the probability that at least 2 consumers in a group of 4 will recognize that brand name of Sony. Give it a try, and I'll show you my answer in 1 second. Okay, and so all I have to do here is I have to build a table that shows for each value of this random variable what the probability actually is. And this table here to the left, I have x's taking on the values 0, 1, 2, 3, or 4, and I associate to each of those values of x the probability. So the probability of nobody recognizing Sony is 0.002, and so on and so on. And this table here, that's my probability distribution. That's all it is. It's just this table. And so to find the probability that x is at least 2, I'm finding the probability that at least 2 people in my group of 4 recognize Sony. So what is that? That's the probability that 2 people recognized, 3 people, or 4 people. So I have to accumulate all of these probabilities together. And so what do? Is I just take the 3 probabilities, I add them up. 15% of the time, exactly 2 people recognized, 39% 3 recognized, and 41% 4 recognized. So I sum this all up, and it actually comes up to about 0.968, which tells me that in English, I interpret this by saying about 97% chance, 97% of the time, at least 2 people in a group of 4 will recognize the brand name of Sony.